Welcome to my science tutorials. In this video we are going to talk about rate of reactions. As the name has already suggests, it's talking about the speed of reactions, the speed of chemical reactions. So let's get started. Now we are talking about speed of reactions. We know that some reactions takes place at a very high rate, that is, they take place with a high speed, something like explosion. When you have fireworks, maybe during Christmas time, you have these knockouts that are going out. There is a very fast reactions, and then we also have reactions that go at a very low pace, like rusting of roofing sheets, and it all depends on some factors that contribute to the rate of these reactions. So today we are going to look at the factors that come to place when it's talking about rates of reactions. Before that, we have to know about two important theories that comes to play when we are talking about rates of reactions. And remember, rate of reaction is also known as kinetics of reactions, and then it is widely studied. So let's look at these theories. The first one is the collision theory, and the second one is the activation energy theory. Activation energy theory. Alright, so let's look at collision theory. What do you think is collision theory? Products don't just come by chance or by magic. They undergo what we call collisions when they are in a reaction. It is these collisions that actually convert the reactants to the products. Now we have the reactants that are in constant collision, but it is interesting to know that it is not all the collisions that result in the formation of products. Therefore, we have collisions that just happen by chance, and then we have the ones that result in the formation of the product, which we are going to refer to as the effective collision. Effective collision. Now, particles are in constant rapid motion, and then it is the most energetic reactants that collide to give us this effective collision that we are talking about. The effective collision we are talking about. It depends on the orientation of the colliding molecule, how it is oriented to form the desired product. So let's look at this. Assuming we have reactant A reacting with reactants B and C to give us a desired product of A, C. What role do you think the orientation of this product, these reactants, will play in the formation of this product? Now let's put the A in this circle. Let's call this A, and then we have B, and then we have C. What does the orientation do? As when we have the A colliding with this reactant from this direction, it's going to result in an ineffective collision. Therefore, we will not have the desired product. So let's call this ineffective. So we will not have our desired product. But then, what if the orientation change? And this way around, we have our B, and then we have our C, and then you have your A from this angle now colliding with this C. It means we are going to have our desired product, which is going to be our our AC, and then we'll have our B standing on its own. So we see that the orientation is what gives rise to the desired product when we are talking about the collision theory, and it's usually known as the head-on collision, which gives us the effective collision. Alright, what is the activation energy theory? Now, this theory says that the reactants in a reaction, they require a minimum amount of energy before they can go over or be equal to the energy needed to overgo the transition state or the complex state to bring about the reaction. So this energy that is needed is what is referred to as the activation energy. The activation energy. It is usually represented by this E subscript A. So this is known as the activation energy. We can look at activation energy by saying that if activation energy increases, let's say if activation energy increases, this will mean that we'll have fewer molecules that will have sufficient energy for effective collision. We'll have fewer molecules that will be able to attain this energy, so it will decrease the rate of the reaction. The fact that when activation energy is high, we'll have a lower yield of product is what brings to mind the study of these factors that will help us to increase the productivity or to have products in great quantity in case we have our activation energy to be very high. So now we'll go and look at the factors that will influence or manipulate the product formation in a chemical reaction. What are these factors that affect the rate of the reaction? The first one is temperature. The first factor is temperature. How does temperature affect the rate of a reaction? Now, when we increase the temperature in a reaction, what it causes is that it increases the kinetic energy of the reactant molecules. You can liken this to, let's say you are boiling rice or beans, and then you put that on fire. As you put it on the fire, you realize it settles, but as a gas burns and then the heat or temperature increases in the pot, what happens is that you start seeing these beans started moving about and vibrating, and this actually sets them or gives them some kind of kinetic energy. It's the same thing that happens in any other chemical reaction. Increasing temperature will also increase the kinetics of the reactants, and this will cause collisions to take place. And if we have collisions taking place, then we can be sure that we also have effective collisions increase as well. So there is how temperature increases the rate of a reaction. So we can say the higher the number of collision per unit time, then the higher the rate of the reaction. So that is temperature. That's what temperature will do. Let's look at this graph. On the vertical, we have the fraction of the reactant molecules, and then on the horizontal is the kinetic energy. So over here, where the yellow is actually the activation energy that is required for the reactants to be converted to, or to pass the intermediate to be converted to products. Alright, so assuming this, the one in the black, the girl line in the black, is the temperature of the reactants, the initial temperature, and then all this area down it we can consider is as molecules which doesn't have the enough energy to to go over the activation energy. So from this area downwards is like the fraction of the molecules that couldn't get activation energy. Alright, so the black one, which is the temperature, initial temperature, has all these areas that couldn't go over the activation energy. But when the temperature is increased to TB, we know that TA is less than TB. So when the temperature is increased, assuming these two bands has the same size, what happens is that you see that as the temperature increases, it allows for more molecules or reaction particles to go over the activation energy. So temperature increases the kinetic energy of the reactants molecules. It makes them greater than the activation energy, and then we have what's increase in products. And once that happens, it increases the rate of the reaction. So that is what temperature does. The second factor is catalyst. Now we know that catalyst increases the rate of a reaction, and then it actually takes part in the reaction, but it doesn't get consumed. So what it does is it creates a new reaction pathway which has a lower activation energy than the original reaction without any catalyst. This graph shows the activation pathways of the catalyzed reaction and the uncatalyzed reaction. So with the first one, you notice that we have activation energy of EA1 for the uncatalyzed pathway, and then we have activation energy of EA2 for the catalyzed pathway, which is in the red. Alright, so you realize that the activation energy for the first one is high. The EA1 is greater than that of EA2 because the catalyst will bring about this new reaction pathway with a lower energy, which means we can have a lot more molecules to overcome the activation energy to give us the product. The greater the fraction of reactant molecules that have their kinetic energy, to be greater than the activation energy, the greater the rate of the reaction. So that's how catalyst increases the rate of a reaction. Now we have concentration. Which also increases the rate of a reaction. Now we know that when the concentration is high, it means we'll have more particles per unit volume. We have more number of particles within the same unit volume. What it means is that it's going to increase the rate of collision. We'll have more particles colliding within a short time. So we have higher collision per time. And once we have higher collision per time, we'll have a higher rate of reaction. So that's what concentration does. We also have surface area. Or let's say the nature of the reactant. The nature of reactants. Now you can think of this like putting a cube of sugar into water. Now it is going to take a long time to dissolve because the surface area exposed to the water molecule is low. But when you grind it and make it a powder, you have increased the surface area, and then you have it to dissolve faster than you have it when it is in the cube form. So when we are talking about the states of matter, we can say that gases have higher surface area. We'll say gases, they have higher surface area than liquids, which surely will have higher surface area than solids. When we talk about solid, we can say about grained solid, which is let's call it powder. The powder solid. Which definitely will be greater than that of lumpy, let's say lumpy. So basically, these are the four main factors that influences the rate of reaction. Aside from that, we also have pressure. But pressure only works with gases. When we have both reactants to be gases, then when we increase the pressure, it means we are compressing the gases, and then there will be a lot more collision, which will eventually lead to increase in effective collision. And once there is an increase in effective collision, that will consequently lead to increase in the rate of reaction. So in this video we talk about the collision theory, where we find out that effective collisions result in the formation of products, and then we also talk about the activation energy theory, where we find out that reactant molecules require a certain amount of energy, a minimum amount of energy, which will enable them to go over the intermediate complex to form products. Now we also look at the factors, and we find out that these factors are temperature, catalyst, concentration, available surface area, and also pressure. And then when we're talking about gases, pressure also are the factors that increases the rate of reaction. So if you like this video, don't forget to subscribe and hit the like button to be notified for the next tutorials on rate of reactions.